Welcome to the ABAQUS Finite Element Analysis. Hi, I am the lecturer in charge for this laboratory demo session.
Today we're going to do a linear static analysis of composite steel structure using one-dimensional element in a two-dimensional space. So, let's get started. Here, we have our composite steel structure supporting a 5 kN per meter of uniformly distributed load. Basically, it's a cantilever steel beam, supported by a steel rod at the tip. The mechanical properties of the steel used in the structure is given. Now, we are going to prepare a finite element model using 1D element, and conduct a linear static analysis. If you are using the ABAQUS software, these are the general procedure for finite element modeling. We will go through the procedure step by step. Let's move to the first section, the part module. In this module, we're going to create part using 1D element in a 2D space. So, what is part? In ABAQUS, part is a geometrical model that represents the physical object. For example, let's say, we have a mechanical component, here. To model this component, we need to create three parts that represent the real thing. Namely, the pump, the gasket and the bolt. The ABAQUS software offers variety of element to model the part. 3D element, 2D element and 1D element. For our example, we're going to use the beam and truss elements to model the composite steel structure. For your information, a beam element can transfer moment, shear, and axial force. However, a truss element can only transfer axial force, either in tension or compression. This element does not hold any flexural stiffness, and it is not recommended for bending problems. The ABAQUS software denotes these elements based on several attributes, such as modeling space, geometric order, and integration formulation. We'll get back on that later. For now, let's move to the modeling of part. In your ABAQUS software, you may open the part module, here. Then, click the icon, Create Part. Name the part as Composite Structure. Choose 2D plana for modeling space. Select the deformable type. And for base feature, click Wire. The approximate size refers to the size of our sketching space. It is best to add the largest dimension of the model. Let's add 3000 millimeters. Then, click Continue. Before we sketch the part, you need to know about the unit consistency in the ABAQUS software. ABAQUS does not recognize any specific unit for all of the parameters used in the model. However, all of the parameters that you defined must be consistent. This table shows the unit consistency to be used in the modeling. For this example, we are going to stick with the unit, millimeter. In the sketch mode, we will draw the whole structure as one part. There are many ways to draw the part. For this example, we're using the coordinate system. First, click Create Line. At the bottom, you are required to enter the first point. For this, we will insert the origin. Next, is the end point. A 2000 mm long beam. Using the same approach, we will draw the 1500 mm steel rod. Once finished sketching, click Done. Next section is the property module. We will define material, profile, section, and beam orientation. The first step of creating a property for the geometrical model is defining the material. For this example, we are using steel material. However, since we are interested in linear analysis, we're only required to enter the elastic data. In the ABAQUS software, change the part module to property module. To define the material, click Create Material icon. Let's name the material steel. To define the elastic property, click Mechanical, hover to Elasticity, then click Elastic. Here, you are required to enter the Young's modulus and Poisson ratio. As a reminder, the unit must be consistent. Since we are using millimeter in the part module, the Young's modulus must be defined in meganewton per meter square. You can edit the created material using the manager here. The next step is to create profile. Profile is the shape and dimension of the beam element. Here are some examples of profiles available in the ABAQUS software. To create a profile, click the Create Profile. For this example, we will be using the eye section. Here, you are required to enter the dimension of the eye section. In the Edit Profile window, you are required to enter the nodal offset, I. Nodal offset is the distance between the center of the wire feature to the local axis of the profile. If you have no need of moving the profile away from the wire feature, it is recommended to use half of the beam depth as the nodal offset. You can edit the created profile using the manager. The next step is to create section. A section basically contains information, such as material, on the geometrical model, or part. For beam element, you need to define the material and profile. For truss element, you need to define the material and cross-section area. To define section, click Create Section. Let's start with the steel beam. Choose the beam type section, and click Continue. In this window, you are required to select the profile and material. If you've created a number of profile or material, you can make this selection. Once selected, click OK. Now for the steel rod. We'll be using the truss type structure for the steel rod. Here, you are required to select the material and define the cross-sectional area. Please note, the truss type section can be used for any cross-section. For example, you have a circular hollow section, and you wanted to use it as a truss member. In the section edit, you're only required to define the cross-section area. You are not required to create profile, because profile is for beam type section. You can edit the created section using the manager. After section has been created, next step is to assign the section to the part. Click the Assign section. It is recommended to untick the Create Set to avoid creating unnecessary set. Then, select the beam wire feature. Click Done. Select the beam section, and click Done. Continue with the steel rod. The final step in the property module is defining beam orientation. Basically, the local axis of the beam is defined in order to change the orientation or position of the profile. To do that, click the Assign Beam Orientation. Select the wire feature containing the beam section. Define the tangent vector. The local axis is displayed. Click OK. If you wish to view the orientation of the profile, click View in the top menu. Then, click Part, Display option. Tick the Render Beam Profile, and click Apply. Here, you can see the rendered shape of the beam element. Next section, the Assembly module. In this module, we'll be assembling the instances. So, what is instance? Instance and part are basically the same. However, part is established in a local coordinates system, whereas instance is assembled in global coordinates system. To understand more about instance, let's take the previous example on the mechanical component. Previously, we know that 3 parts are created for this mechanical component. If we want to establish the mechanical component in the assembly, we need to insert 1 pump instance, 1 gasket instance, and 8 bolt instances. All of these instances are recalled from the part module. These instances are then assembled and arranged accordingly in a global modeling space to form the mechanical component. In the ABAQUS software, you can access the assembly module here. To insert an instance in the assembly, click Create Instance. Since we have 1 part only, the part will represent the whole structural assembly or instance in our model. For instance type, keep dependent, then click OK. The next section is the step module. In this section, we'll assign suitable analysis procedure and request relevant analysis output. The analysis procedure is selected based on step. In ABAQUS, there are generally 2 types of step: initial step and analysis step. The initial step represents the condition at the beginning of the analysis. We usually define the boundary condition using this step. Also, the initial step is created automatically, and you cannot edit this step. The analysis step is the analysis procedure that must be defined by the user. Basically, it should be based on the type of analysis that you wanted to execute. You can access the step module here. To create an analysis step, click Create Step. For this example, we'll be executing a linear static analysis. The suitable analysis procedure is the static linear perturbation. You can find the analysis procedure under the linear perturbation type. If you wish to edit the created step, click the Step Manager. You can see that the initial step has already been created and cannot be edited. Next step is to request the analysis output. There are 2 types of output in ABAQUS. the field output, and the history output. For this example, we're going to focus on the field output only. Here is some example of output that you can request from the analysis. The output request is located under the step module. You can access the field output in the manager, here. Please note, once you have created a step, the field output will be automatically created. Click Edit. In here, we can see the pre-selected output. Reminder: the number of outputs will affect the analysis burden later. The more outputs you request, the longer the analysis will be. Let's request the section forces and moments. Also, the history output has been automatically created. You can view it in the History Output Manager. Next, we're going to move to the Load module. Before we go into the Load module, let's review the degree of freedom. In ABAQUS, the degree of freedom, or DOF, is labeled numerically, as shown in this figure. Note that axis 1 is the x-axis, axis 2 is the y-axis, and axis 3 is the z-axis. This is the convention used in the global coordinate system. Also, ABAQUS recognize U as translation and UR as rotation. These are some example of DOF for a common support condition. The ABAQUS software offers a variety of load types and boundary condition for the analysis. Here are the suggested loads and boundary conditions that you can use for 1D element. Now, let's create load and boundary condition. Access this module, here. To create a load, click Create Load. Name it as UDL, and choose the line load type, under the mechanical category. Select the region to assign the load to. We're going to assign 5 kN per meter on this region. Based on the unit consistency, the load shall be taken as 5 Newton per millimeter. Then, click OK. You can view the created load at the Load Manager. To define boundary condition, click Create Boundary Condition icon. Let's create a fixed support for the beam. Please ensure that the step is taken as initial for the boundary condition. Then, select the displacement rotation type, and click Continue. Pick a node to assign the BC, and click Done. Select suitable DOF for the fixed support, and click OK. Do similar procedure of the pinch support.
Let's us move on to the next module, the Mesh module. Previously, you have been introduced with 2 types of 1D element. These elements must be assigned to the wire feature before running the analysis. In ABAQUS, open the Mesh module. Select Part, choose the part that we wish to change its element. For this example, we only have one part. If you have multiple parts, you can locate them here. Click the Assign Element Type icon. Let's assign the element of our steel beam. As you can see, the beam type element has been assigned to the wire feature. You may also change the geometric order and integration formulation here. By default, ABAQUS assigns the shear flexible formulation for the beam element. The shear flexible formulation adapts the Timoshenko beam theory, which is suitable for high shear problems or large deformation state. For this example, we're going to choose the cubic formulation, which adapts the Euler beam theory and suitable for elastic beam analysis. At the bottom, you can see the denotation of the beam element, which is B, 2, 3, which means a 2-node cubic beam, in a plane. Let's assign the element for the steel rod. Search for the truss element. And here, you can see the denotation for truss element. After assigning the element, the next step is to seed the model. Seeding is the process of discretizing model into a finite number of elements. The size or number of elements is defined during the seeding process. In ABAQUS, seeding can be done either by part or by edge. For this example, the seed by edge approach is applied. This is because we wanted to have a variety of seed sizes on one part. This cannot be achieved if we are using the seed by part approach. Let's seed the steel beam first. In the module, click on the Seed by Edge icon. Select the steel beam wire feature. For the steel beam, we will seed it by size. The ABAQUS has suggested the seed size of 200 mm for the wire feature. You may change the seed size accordingly to suit your model. It is recommended that you conduct the mesh sensitivity analysis to determine the suitable seed size for your model. This analysis, however, will not be covered in this example. For the time being, we take 200 mm as the seed size for the beam. Click Apply. A number of purple dots will appear on the wire feature. These dots represent the node of the wire feature, and in between the nodes is the beam element. For the truss element, it is recommended that the wire feature is assigned with one element. For that, we'll seed the steel rod wire feature by number. Take the number of elements by 1 and click Apply. As you can see, only 2 purple dots appear in the steel rod wire feature. This shows that only one truss element exists. The final step of the mesh module is to mesh the model. To do so, you can click the Mesh Part icon to mesh the whole part. The model has turned light blue if the meshing is successful. The final step is to create a job. In ABAQUS, you can find this in the Job module. To create a job, click the Create Job icon. We name it as Main Analysis. Then click Continue. And OK. Before running any analysis, it is suggested to locate the work directory for this model. Basically, a work directory will hold all the analysis output of your model. It is best if you know where the analysis output is located. To change work directory, go to File, then click Set Work Directory. Click Browse to assign a folder in your computer. By default, the ABAQUS will store any analysis output in your local disk under the temp folder. Click the Job Manager. Before running the analysis, it is best to data check to locate any modeling error. Once data check is completed, click Submit and wait for the analysis to be completed. To view the analysis output, the visualization module is used. In this example, we'll cover the field output using the contour plot and symbol plot. In ABAQUS, to view the analysis output, click the Results. It will redirect you to the visualization module. The viewport will display the undeformed shape of the model. To display the deformed shape, click this icon. To plot contour on the deformed model, click this icon. The contour on the model represents the miser stress. Each color represents a value as denoted in the legend here. The viewport is showing the miser stress contour plot. You can display other field output here. Please note that the field output must be requested in the step module. If you wish to change the contour plot in an undeformed shape, click and hold this icon, then click the undeformed icon. The contour plot can also be displayed as a scaled plot. To do so, click the contour plot option. Then check this item and click Apply. In the viewport, you can see that the field output section moment is displayed as a scaled plot, similar to a bending moment diagram. You can also request the maximum and minimum value of the field output from the plot. Under the Limit tab, tick these two items, then click Apply. The maximum and minimum value are shown in the viewport. Another possible way to view the field output is by symbol plot, which is located here. This plot displays a color-based arrows that signify the value and direction of the field output. In this current viewport, it shows the axial stress in the section. The symbol plot is useful in showing the direction of the deformation, and also reaction forces. You can also display it in an undeformed shape. That is all for this example.